The next paper is a contribution from Virginia Tech. The title is Alkali Modified Zeolites, Novel High Surface Area Base Catalysts. Authors are P.E. Hathaway and M.E. Davis, and Paul Hathaway will present the paper. Do you have slides? Do you have slides? Yeah.
As you know, there's been a lot of work and emphasis on the development of zeolites as acid catalysts. Our work was emphasis on designing a zeolite which showed base catalysis. We wanted to develop it and characterize it so that a catalyst with high base activity as well as selectivity can be developed and used for other reactions. The outline for this talk will be twofold. Firstly, development of the basic phlogisite-type zeolite, which demonstrates the high base activity and selectivity. And secondly, the elucidation of the active base type. So why basic zeolite, specifically the phlogisite type? Well, we want shape selectivity. Phlogisite structure is shown below. We want shape selectivity by virtue of the pore size, approximately 7 to 8 angstroms. It's a high surface area material, between 500 and 900 meters squared, depending on the unit composition of the zeolite. And thirdly, it offers a large pore volume. The characterization of these zeolites is kind of an elusive thing to do as far as trying to do what's the strength of the base or the acid site. We looked at isopropanol decomposition in a parallel reaction pathway to acetone and hydrogen. Looking at this as our base indication, we're looking at acetone rate versus propylene rate. So as we have high acetone rate and hydrogen, we have indicative of strong base selectivity. The propylene is usually indicative of a Bronsted acidity by elimination. However, there's considerable evidence to show that propylene can be formed over solid bases as well, and we'll elucidate on that later in the talk. Some of the advantages that can be done at reaction temperatures and under steady state conditions and the ease of analysis. Some of the disadvantages is that at the secondary alcohol, if we change that to say a primary alcohol, say 1-propanol, we might change the activity as well as the selectivity, and again change our interpretation of the base characteristics. And second, it's not there definitive in the sense, again, we mentioned that some of the propylene might be behavior of the base sites. And thirdly, it's not distinguished between base strength and base number as, say, titration might. Catalyst variables we looked at when we started this work were the silica-alumina ratio. We looked at the X type versus the more salacious Y type. The exchange cation with group 1A metals, lithium through cesium, and the exchange salt, hydroxide, acetate, nitrate, and chloride. And fourthly, the absence and presence of these exchange salts in the zeolite. And quickly, our best catalyst that we came out with was in fact the Y type and not the X type. Our particular catalyst had a silica to aluminum ratio of 2.34. The cation we preferred was the cesium, and the exchange salts we found were the hydroxides, the acetate, and nitrate. That's taking the sodium Y to the respective cesium Y. We found very poor results with the chloride. And the most important point was the impregnation of the zeolite. This is what really added to the base activity. We did on an effective loading of approximately 2 cesium acetates per unit cell into the zeolite. Impregnation was done by mixing the cesium Y in an aqueous cesium acetate solution and evaporating off the water, leaving the acetate squared onto the Y zeolite. Physical chemical data, I wanted to illustrate 3 catalysts that we used here. Where a partially exchanged Y, say a fully or maximum exchange Y, there's inaccessible sodium cations located in the sodalite cages that cannot be reached by the cesium for exchange. And a partially exchanged X zeolite. X zeolites are typically difficult to fully exchange. So there's approximately about 10 sodium cations here available for exchange. So during an impregnation with an aqueous solution of cesium acetate, there's a possibility that some of these sodium cations can exchange with the impregnated cesium acetate to form sodium acetate, and thus work against us as far as impregnation. So I chose a partially exchanged Y so that we have some available sodium cations as well to see if in fact they are exchanging during impregnation. The respective exchange, the molecular weight increase, you can see as you get to a heavier composition, which draws an important point that you see a relative weight increase to X. So when we're normalizing our rates to, again, give us an indication of the acid and base properties, we don't want to do it on a weight basis because you can see X is 25% heavier per unit cell. So we normalize all rates on a gram mole of unit cells, which is comparable to a volume basis. And we've located, again, on average, 2 cesium acetate molecules per unit cell on each of these materials. First indication we get that something, in fact, is different between the X and the Y materials. From differential thermal analysis, we're looking at the exothermic being upward and the endothermic being downward. Again, our 3 materials, the impregnated X with maximum exchange Y, and the partially exchanged Y, and a cesium acetate sport on silica at a comparable weight loading. See the endothermic loss in water for all 4 materials. But you see with the X material, there's not really much definition in the exothermic decomposition of the acetate. Quite a broad shoulder there. However, you see for the Y, significant sharp exotherm occurring at about 450 degrees, 475 degrees. Again, indicating that something particular is particularly happening between the Y material and the X. And for the cesium sport on silica, again, it's completely different. So again, first indication that perhaps something is occurring on the Y zeolite. Looking at the respective rates, again, we're looking for acetone rate being comparable to the base activity. Here we're doing at 350 degrees measured at differential conversions. Again, we're looking at a unit cell basis, the acetone being the blue bars and the propylene being the white bars. For the X material and the Y material, their first significant difference, you see an order of magnitude increase between the Y material and the X material. It might further add that without impregnation of this material, the activity is comparable to the X, so it would only be up here. So all this other activity is presumably due to the impregnation technique. Again, another point is that the selectivity for this material is over 97%, whereas for the X material, it's only around 60%. And furthermore, the partially exchanged Y is active as well, suggesting that these sodium cations are in fact not exchanging during impregnation. We wanted to get a feel for how well we're doing as far as activity, so we looked at a characterization of magnesium oxide, which is considered a solid base. We're comparing here on a surface area basis at 350 degrees, again measured at differential conversions. Our Y material and magnesium oxide, they're comparable in activity as well as selectivity. We move to a volume basis, which may be more applicable, say, to reactor design. We can see for our material, again on a volume basis, is significantly better than magnesium oxide. So it gives us a relative feel how well we're doing as far as activity and selectivity. So at this point, we conclude that it appears for the impregnated Y zeolite, a highly active base site is generated from the decomposition of the cesium acetate. And as a redevelopment, it gives us an exceptional activity as well as selectivity. It gives us high surface area material. And thirdly, gives us potential for shape selectivity, which we are currently working on in our laboratories now. This moves us into the second part of the talk, the elucidation of the active site. We have cesium acetate supported on the Y zeolite and thermally decomposing it to what? The possible candidates we considered were cesium metal, cesium carbonate, and cesium oxide. Simply from ESR spectroscopy, we saw no evidence of the cesium metal. And secondly, when you calcine material in oxygen, where we would expect a high affinity of the cesium with the oxygen, the activity was not eliminated. So it suggests that the cesium metal is not involved in the catalytic activity. Cesium carbonate, well, there was no evidence from the carbonate species from IR after calcination. And secondly, bulk cesium carbonate was inactive in isopropanol decomposition. Which moves us thirdly into cesium oxide. I'd like to draw 2 points from this particular figure. These were bulk cesium oxide and our supported cesium acetate on Y materials done at 350 degrees acetone yields. And the point is, firstly, that cesium oxide, in fact, is active in isopropanol decomposition of acetone. Secondly, we see a similar startup behavior. You see this one deactivates over a period of 3 to 4 hours, and after a period of 8, completely gone. However, you see a deactivation up to 4 hours, and then a steady state occurring for our Y material. So for cesium oxide, we see a comparison between the impregnated Y zeolite and the oxide, similar startup kinetics, similar acetone selectivities at around 99 and 97 for the oxide and impregnated Y material respectively, and this is not representative of all oxides in alcohol decomposition, specifically isopropanol. And thirdly, as I mentioned earlier, it's slightly more active in an atmosphere of oxygen calcination, where we expect the oxide to be a final result. You can see the values down here. It's slightly more active than in a helium atmosphere. So at this point, it appears that we have a cesium oxide located on the zeolite. But I'd like to go just a step further and provide just further evidence for occluded cesium oxide. And this is by first reviewing a proposed mechanism for base catalyzed decomposition of isopropanol over a bulk metal oxide. And then once we establish that, just to illustrate similarities in the observed kinetics between the bulk metal oxide and our cesium Y material. So the suggested mechanism for alkyl decomposition over magnesium oxide would be a dissociation of the OH group to form an isopropoxide intermediate as well as a hydroxyl group. Abstraction of the alpha hydrogen would result in acetone and hydrogen, and as I mentioned earlier, abstraction of the beta hydrogen or a breakage of the CO bond would result in propylene. So if this type of elimination or decomposition is occurring, then we would expect an electrophilic adsorbate like CO2 to poison both reaction pathways. If the propylene was independent of the base, then it would continue, we would expect, just based on a Bronsted acid site, for example. So in fact, we followed experiment. This is acetone and propylene. Here's the acetone activity and propylene activity from magnesium oxide. We see, firstly, similar startup kinetics for both the acetone and propylene. The selectivity was well over 97% at a standard deviation of less than 0.1%. So the whole time it's maintaining that selectivity, suggesting some relation between the acetone and propylene relation, activity. We pulse CO2 at constant partial pressure of isopropanol, and in fact we do suppress both the propylene and the acetone formation, remove the CO2, and we're back up to steady state. Again, it appears that the reaction suggested back mechanism is somewhat correct here. Looking at our material, again we see similar startup behavior between the acetone and the propylene, less than 2%. 0.2% standard deviation between the whole time. We pulse CO2, and again we suppress the acetone activity. However, we promote the propylene activity, which is not consistent with our proposed oxide decomposition mechanism. However, there's some earlier work by Folletti and Munns back in '65 on promotion of propylene formation over sodium X by the addition of CO2. Here we have isopropanol conversion of propylene as a function of the CO2 partial pressure. And you can see as we increase the partial pressure of CO2, we have an increase in the propylene formation. So what we suspect was happening is, in fact, a little schematic here, possible influence of CO2 on propylene formation is, in fact, two separate sites producing propylene. Perhaps a site 2 from CO2 promoted type, and site 1 being an isopropoxide type result, propylene coming from an propoxide intermediate. So if we work, what we probably were is up in this higher partial pressure of CO2 where we're well above the steady state activity. So what we want to do is go down to a lower partial pressure where we eliminate the promotion in propylene activity, and hopefully we can see the suppression in propylene activity due to an isopropoxide intermediate. And in fact, that's what happened. When we looked at acetone and propylene yields at low partial pressures of CO2, this is P over P naught 10 to the minus 5. Here's the acetone yield and the propylene yield. You can see the selectivity remains absolutely constant until we start getting higher partial pressures of propylene, again suggesting a propoxide intermediate. So to draw some conclusions, firstly, earlier in talk, at equal loadings of cesium acetate, the acetone activity for the impregnated Y zeolite is significantly better than the X material, equally prepared X material. Secondly, the decomposition of the cesium acetate supported on Y appears to be cesium oxide due to one, similarities in the startup kinetics, the acetone selectivities, and thirdly, kinetic behavior, similarity between bulk metal oxide and the impregnated Y zeolite. And thirdly, there's no variation in the acetone to propylene ratio at low partial pressures of CO2. This suggests that the cesium acetate impregnated material isopropanol decomposition proceeds by an isopropoxide intermediate to both acetone and propylene formation. And just to acknowledge an NSF-PYI grant to Professor Mark E. Davis with matching money coming from the Dow Chemical Company. Thank you very much.
You said that you prepared a cesium acetate on silica at comparable loading.
Yes.
Did you carry out the similar experiment?
Yes, it was completely inactive.
Okay, somebody talk.
All right, do you have any clue why the X is different from the Y? If it's really the impregnation procedure, it seems like it's difficult to understand why it's so different.
Yeah, it is. One suggestion might be the X may be a weaker material. It may be decomposing the structure or reacting with the structure instead of going to an oxide. We don't really know at this point, but it's interesting. I can't give a good answer for that.
Is cesium located inside the cage or outside? What kind of it is?
As far as its location after decomposition? I guess there was a talk earlier looking at magnesium acetate on HDSM5 and showed a covering on the outside. There's 3 points you could address. That firstly, if this was the case, it was just on the outside and no influence of the material, then we would expect X and Y to be similar. Secondly, I've done higher loadings of cesium hydroxide, which behaves similar to the acetate, and we completely eliminate the activity. We wouldn't expect that if there was no involvement of the porosity. Thirdly, supported on the silica, there was no activity, as I addressed the question earlier. So it appears that it's probably inside, and there might be some influence of the zeolite on the decomposition, per se, a catalytic decomposition. But we don't know for sure.
I had the same question.
Okay.
Yeah. Very good.
Thank you for your
Thank
attention.
you.